A very good day to my internal examiner, Dr. Noor Wayu, and my project supervisor, Dr. Kaur. My name is Frederick Chong, and I am currently majoring in the process analysis and control course specialization. The title for my final year project is Predictive Modeling for Base Oil Properties, and this is a collaborative work with the Petronas project team. Here's the flow of my presentation today. I will first briefly introduce the background of this work, and then stating a problem statement, objectives, as well as my proposed strategies. Following that, I'll screen through my findings to support my proposal, and then going through the scope of this work, and finally concluding my presentation by summarizing the content presented as well as to update my progress. So here's the project introduction section. To begin with, what is base oil? Base oil is essentially lubricants without the additives. Base oil may have many grades, which are mainly defined by some of these key properties, namely KV100, which stands for kinematic viscosity at 100 degrees Celsius. VI stands for viscosity index, pour point, NOAC, and CCS stands for cold cranking simulator. The base oil production process can be categorized into three main sections, namely the crude distillation unit, vacuum distillation unit, as well as the MG3 section, which is basically the finishing section for the base oil production. The raw crude oil, after passing through the desalter unit, will enter the CDU. CDU fractionates the raw crude oil into a variety of products at atmospheric pressure. The bottom residues of CDU, which cannot be cracked at atmospheric pressure, will then enter the VDU to further break down the heavier hydrocarbons at vacuum conditions. The three side draws coming out from the VDU are mostly base oil, which will combine with some of the CDU bottom residues and the unconverted oil stream and enter the MG3 section for treatment to meet their respective product specification. And these are the 6 key parameters which we want to predict in this work. Given the background knowledge of this work, here's the problem statement. Due to the pandemic, there has been much fluctuation in the lubricant market, and this drives the need to optimize the base oil production process. Besides that, standard process simulators such as Aspen HYSYS cannot accurately model the lubricants due to the presence of waxy solids. And moreover, lab analysis for base oil properties measurements, such as viscosity, for example, is often time-consuming and costly. All of these factors give rise to the need for this work, which is to build a predictive model to predict ahead of time the base oil yield and other properties, the 6 key properties, which then allows necessary actions to be taken to control production accordingly. Currently, there has been individual models developed for each of these individual sections to predict Y from X, Z from Y, and W from Z for CDU, VDU, and MG3 respectively. Hence, the main objective here is to develop a statistical model to predict the base oil yield and other properties based on the CDU data. This means ultimately we want to predict W from X directly. So one can imagine this as a gigantic block instead of 3 distinct smaller blocks. Secondly, the aim is also to optimize the current developed models, these individual models, to improve their prediction accuracy and precision. So the proposed solution here is first to integrate the CDU, VDU, and MG3 models into one single model, thus being able to predict W from X directly. So we want to integrate these 3 models into a single model. Secondly, is to tune the model hyperparameters to their optimal values. So each of these individual models, we would wish to also tune the hyperparameters to boost up their respective accuracy. Hyperparameters are basically the parameters within an algorithm to tune the model, which I'll explain further in the subsequent sections. So by developing a statistical and predictive model, the problem stated can be resolved. Now I shall present a literature review on supervised and unsupervised learning algorithm, and here's an overview of it. For this work, we will be looking at supervised learning under regression tasks, and we'll explore three main functions under regression, which are linear regression, decision trees, and artificial neural network. Also, besides that, to understand how variables interact with one another, I'll also explore other functions such as the principal component analysis. Here's a past work done in comparing certain regression methods for lubricant properties prediction. Variable selection, penalized regression, and latent variable are linear regression methods, while neural network is a non-linear regression. Take, for example, density at 15 degrees Celsius of base oil. It seems that all of the regression methods, linear and non-linear, performs very well in terms of their prediction performance because they have an R-square of over 0.95. However, when we take a look at the viscosity properties, KV100, for example, we see that the linear regression methods performance drops steeply. However, neural network continues to perform at best at 0.997 and manage to predict accurately. So from this literature, we can conclude that neural network performs is a suitable algorithm to be used for this analysis work. Another comparison framework done is the prediction of dead oil viscosity. This framework compares 5 learning algorithms, which are superlearner, light gradient boosting machine, random forest, extreme gradient boosting, and multi-level perceptron artificial neural network. Here, so we look at 3 main statistical measures, which are R-square, mean absolute, and root mean square error. Overall, we see that in terms of R-square, superlearner outperforms other learning algorithms. However, the XGBoost gives the lowest error among all the learners. It is also worthwhile noting here that no one algorithm is definitely better than the other in terms of prediction performance. The algorithms used is largely dependent upon the data set. So some algorithms may fit better for certain data set, but not others. In summary, there have been many researches done on these learning algorithms, even in the petrochemical industry, and even attain a moderate to high level of accuracy of prediction. Hence, it is feasible to predict likewise the base oil properties as in the case of this work. Moving on, I have now screened through the scope of work for this project and the tools utilized. Here's the tentative but almost standard scope of work for most statistical modeling work. I've segregated them into 4 main phases, denoted by the 4 different colors here. The first phase involves the data gathering phase, and the first step is the data collection step, which is done by the Petronas project team. Here, the main thing we need to ensure is that all the potential predictors as well as the targeted response data are pulled accordingly with an accurate timestamp. What I mean by this is that, take for example, if we want to pull the lab data for viscosity, and the lab data for viscosity is out at 2 p.m., while the lab sample is actually collected at 12 p.m., then all the other process parameters data that we want to pull should be 12 p.m. instead of 2 p.m. So this will largely affect the accuracy of the model as we develop in the later stage. The data are collected on an Excel sheet, and then using R programming, we'll read the Excel file to store the data set, and then some data pre-processing steps are done, such as filtering of outliers. We now have a good data set to begin with for our analysis. And the first step in the analysis is usually to screen through the correlations of the process parameters with the targeted response using various statistical functions such as the multivariate and the p-value analysis. These screening functions indicate the hierarchy of importance of each predictor's contribution to the prediction of the targeted response. So with these functions, we then shortlist the predictors and form a new data set with a targeted response. Then split the data set into training and test set in 70:30 ratio. The next phase is the model development phase. For this work so far, we have only utilized the extreme gradient boosting algorithm to develop our models. Then the algorithm hyperparameters are tuned accordingly to an optimal combination of hyperparameters. Then using the tuned hyperparameters, we now formulate a new model and retrain the model. The last phase is the model validation phase, where the results are validated by checking certain statistical measures such as R-squared, IMSE, and by visualizing certain diagnostic plots. An importance plot is also generated featuring the rank of importance of each predictors. And lastly, the model is saved as a .model binary file format, which is the desired final product by the Petronas project team. With all that is being mentioned here in this workflow, certain steps have to be reiterated to develop a better model. So here are some examples of diagnostic plots generated in GMP. On the left-hand side, we have the actual by predicted plot of both the training and the test set generated by the boosting algorithm. Here it seems that the training set performs way better than the validation set, as seen by the scatteredness of the data points along the fit line. This is an indication of the model overfitting, and it requires a more optimal tuning of the hyperparameters. On the other hand, we have diagnostic plots for the neural network algorithm, and from a quick glance of it, we may infer that the neural network model performs poorer as compared to the boosted tree algorithm. Besides visualizing the actual by predicted, we might also want to visualize other plots such as the residual by predicted, where residual is basically the difference between the actual and the predicted. So typically, we will want to observe the data points randomly scattered along the residual equals to 0 line. But over here, we observe a certain pattern. There's a pattern here on the data points, which may indicate a bad fit of a neural network model. So from this slide, we may tentatively conclude that the gradient boosting algorithm is a more suitable algorithm used for this analysis than a neural network algorithm. Here are some of the plots generated by RStudio using extreme gradient boosting algorithm. And the importance plot here features the hierarchy of importance of each predictor from the greatest to the least. I shall now conclude my presentation by summing up all that I've presented and updating my progress. So here's a book and an author once wrote, forget dieting, it's all about data-driven fueling. Eliminate the guesswork, gather data for your individual body and understand how blood sugar affects your weight. The crux of the message here is that the nature of this task mostly is data analytics and data science. And as stated, market fluctuations, inaccuracy in fundamental models by simulation, as well as the time-consuming and costly lab measurements poses challenges to the base oil production process, which gives rise to the need for this work. And so by developing so-called soft sensors, or software-based sensors, this will help improve overall process health and visibility, since a continuous and predictive measurement is available, which allows necessary actions to be taken to control the production to our desired output. Moreover, as we have seen that past work has shown that machine learning algorithms are capable of predicting accurately the oil properties and market, thus affirming that the proposed strategy for this task is feasible. And for this work, RStudio is complemented with GMP to conduct the analysis. Here's the timeline for this project for this semester. A fairly large portion of the time was spent at the beginning to thoroughly understand the background and the scope of this work. And the rest are the technical work involved for the remaining weeks ahead. This is just a tentative timeline since some of these steps here may have to be reiterated as mentioned. I've now come to the end of my presentation. Thank you for listening attentively. If you have any questions, feel free to bring them out during the Q&A sessions, and I'll see you there. Thank you.